Hello, ladies and gentlemen. Today we're going to be talking about different ways that we can calculate measures of variance. We've already talked about standard deviation and variance as calculations to measure different ways of that variation or spread of our data, but we're going to add to our toolbox of calculations for measures of variance with two more calculations. The first one being CVars, or coefficients of variance, and then the range rule of thumb. So what you'll need today is your notebook, your foldable, hopefully with your notebook, and then a pen or a... So the first calculation we're going to go over today is the CVars, or the coefficient of variance. This shows how similar the different sets of data are that can measure different things. So CVars only make sense when we have two completely different sets of data. Like maybe one of our sets of data is talking about age and the other set of data is talking about height. Those are two different variables that we're measuring, age and height. And what CVars is going to do is give us a comparison between the two to see which one is more variable or less variable. So it's easy to compare two standard deviations of two data sets that are talking about the same kind of variable or unit. Like if we were talking about two different data sets that represented temperature, but let's say those two data sets were representing two geographically different locations, we're still talking about temperature, so it's easy to compare standard deviation between the two geographical regions. But like I said, if we were talking about age and height, that variable is not the same, so it's not easy to just find the standard deviation of both of those and then compare the two. It's better for us to use the coefficient of variance when comparing two totally different sets of data that are measuring different variables. So our formula for CVars is going to be the standard deviation divided by the mean, and then it's a percentage, so then we have to take that decimal times 100%. All right, let's look at an example of how to use CVars and the formula. So in this example, we're talking about the sales of automobiles or cars. The mean number of cars that were sold over a 3-month period is 87 with a standard deviation of 5. The mean of the commissions on all of those cars is 5,225 with a standard deviation of 773. Compare the variations of the two different data values. So when we're talking about these two different sets of data, they already found the mean and the standard deviation for us, so we didn't have to do that from the raw sets of data. But those two raw sets of data are comparing two different things. They're talking about numbers of cars sold and the price for the car salesman on their commission. So we're talking about price and number of cars sold. So we can't just straight up compare 87 to, or excuse me, the standard deviation 5 to $773. It doesn't make sense to make that comparison because it's two totally different units of measure. So we're going to use the CVars formula, the standard deviation divided by the mean times 100. So I will do the number of car sales in red. So our CVars for that will be 5, our standard deviation divided by our mean, which is 87, times 100, punch that into our calculator, we should get back a percent of 5.7. I'll grab a different color here. Let's do blue for the commissions CVars. So again, the standard deviation is 773 divided by the mean, which is 5,225. All times 100 will get us a percent of 14.8. When they say compare the two, all we're trying to say is that the commission's CVars percentage is the one that is more variable. More variable. So the higher the percentage between the two, that data set is more variable, or the spread is farther apart for the commissions than it is for the sales of the car. That's all they wanted us to do with the comparison. All right. Now we're going to move on to, that's it for CVars. That was that easy for that formula or calculation. So now we're moving into the second one, which is range rule of thumb, which is an estimation for standard deviation. It is a very broad approximation of standard deviation, and it's based on the principle of the normal bell curve of the 95%, which we'll get to in a couple of lessons. But what the calculation is for the range rule of thumb it's an approximation for standard deviation. That's why it's S is approximately the range divided by 4. So let's look at an example. It says, given this data set, so these data values, find the standard deviation using the range rule of thumb, and then also find the standard deviation, how we always do using our calculator after we learned that shortcut. So first we're going to find it using, I'll grab my Ren pen again. We're going to find it using range rule of thumb. So the range divided by 4. It looks like my data values are arranged in order. So my range is my highest minus my lowest, 13 minus 5, all divided by 4. 13 minus 5 is 8, divided by 4. My standard deviation, according to the range rule of thumb, is 2. Let's go to our graphing calculator then and find the standard deviation using our graphing calculator. So let's go into our list. Oh, let's clear my list first. 4, clear, list 1. Sweet. Okay, now I can go into edit. So it's 5, 8, 8, 9, 10, 12, 13. Go back to our stat button, hit calculate. We want one variation stats, one var stats. We were in list 1, and then we're looking for SX, which is our sample, and that's 2.69-ish over here. So SX was 2.69. And so when they say compare it to the 2, we just have to write down both of them. So that's that. All right, oops. Why do we need that range rule of thumb approximation if we know how to do the standard deviation now? Like maybe we can understand in the world of mathematics that the range rule of thumb was used chronologically before the real calculation of standard deviation ever came into place. But why would we use it now? So it's used to estimate the largest and smallest values in our data set, or that mean and, or excuse me, that minimum and maximum. So the estimated minimum value will be the mean minus 2 standard deviations, and the estimated maximum will be the mean plus 2 standard deviations. So remember how we said range rule of thumb was an estimation based on that 95 or normal curve rule. So we're going to get into the bell curve eventually here, but the bell curve is the normal distribution, like we talked about in Unit 2 when we talked about shapes of distribution. And so what they're saying is on the bell curve, your mean is going to fall in the middle, and they're saying your anticipated minimum will fall 2 standard deviations below, which is why we're subtracting from the mean to the left of the mean, and your maximum will fall 2 standard deviations above or to the right of the mean. So what they're saying is that everything within this range in your normal bell curve is normal. That's why it's called the normal curve. And then everything that falls outside of that usual or anticipated estimated min and max would be unusual. Okay, so anything that falls above or below that minimum and maximum value would then be deemed unusual, or what we also call outliers. So that's why we would use range rule of thumb, is to anticipate those values of the min and the max. Let's look at an example. So it says using those two values to find the minimum and maximum, let's find the min and max given the mean is 10 and the range is 12. So we want to find the minimum value, which is going to be the mean minus 2 standard deviations. I'll put SD here. And the max is going to be the mean plus 2 standard deviations. We know that the mean is 10, and they didn't give us the standard deviation. They gave us the range. But we know that we can anticipate or guesstimate the standard deviation given the range using the range rule of thumb. So it would be 12, that range, divided by 4, which is 3. So when it comes to finding the min, then we're going to plug in what we found with the standard deviation and what we know with the mean. So our mean is 10, our standard deviation is 3, so that minimum value is going to be equal to the mean, which is 10, minus 2 times that standard deviation that we found of 3. 2 times 3 is 6. Excuse me, had a little hiccup there. 2 times 3 is 6, so 10 minus 6 then would be 4 for our minimum value. And we don't even really have a context for this data set. We just know that it's a number. So I was going to give it a unit or a label, but I guess we don't have one. So we're just going to go to finding the max for this ambiguous data set. The max then would be that mean number plus 2 standard deviations. So that'd be 2 times 3 for those standard deviations. So that's 10 plus 6, which is 16. So our minimum value is 4, and our maximum value is 16. So again, thinking about the bell curve, that picture that we drew on the last, ooh, that was a bad bell curve. Let me redraw that. Just like on the last slide, there we go, that's a better bell curve. That mean or average was 10. So then 2 standard deviations above or to the right for that maximum value was 16, and 2 standard deviations below was 4. So we're saying anywhere between 4 and 16 for this data set is deemed normal, and anything that falls outside of that range, 4 to 16, would be deemed unnormal. Which makes sense. When we say we're going 2 standard deviations to the right, we added 1 standard deviation, added another standard deviation to get to that 16. If we subtracted 1 standard deviation and subtracted another standard deviation, we would get down to that 4. Let's look at another example. So it says, using the 40 chocolate chip cookies, or chocolate chip counts for Chips Ahoy cookies, the mean is 24 chips and the standard deviation is 2.6. Where this data actually came from was, about 4 or 5 years ago, I actually brought in some Chips Ahoy cookies packages, and we found by going through and breaking up all the cookies what our mean and standard deviation was for a given random Chips Ahoy cookie. The mean was 24 chocolate chips and the standard deviation was 2.6. So the question is, using the range rule of thumb to find that min and max, usual numbers of chips. We want to find the min and max number of chips, and then it's going to ask us, is a cookie with 30 chocolate chips unusual or usual? So first we're going to find that min and max. So that minimum value is going to be equal to the mean minus 2 standard deviations. So the mean was 24 again, minus 2 times that 2.6 standard deviation, which, plugging it into our calculator, is 18.8 chocolate chips for our min. Our max is going to be that same mean, 24, plus 2 standard deviations, so it's going to be 2 times our standard deviation was 2.6. So that will be 29.2 chocolate chips for our max. So 18.8 to 29.2 is deemed normal for any given chocolate chips Ahoy cookie. So they said, would a cookie with 30 chocolate chips be unusual? Yes, it would be. 30 chocolate chips falls outside of our usual range. Usual range. That would be a very unlikely cookie for you to get, is 30 chocolate chips in one Chips Ahoy cookie. Okay. With that, I want to thank you all for taking good notes. Those were our 2 different calculations for different ways we can measure measures of variation or spread. So make sure you have all this stuff written down. And I want to thank you for taking good notes, and I will see you soon.